Hi, my name is Bob Kubinek, and I helped design the elicitcausal app, which hopefully you're interested in using, and this video explains how to use it. Now, the purpose of this app is to allow you to design a causal graph. These have become increasingly popular in research design for many different reasons, including causal identification. The purpose of the elicitcausal app is to allow you to design a causal graph that incorporates all of your theoretical priors. So if you're trying to understand something like people's vote choice, or how they choose a partner, or any other outcome, you take all the knowledge you have about the factors that predict that outcome and you can put it into a causal graph. And the specific purpose of the elicitcausal app is to allow you to define such a causal graph, but also to do comparisons, with the idea being that you would put together a causal graph before doing a study that incorporates all your knowledge about how variables are related to each other. You do the study, and then you update the causal graph with your new information, right? Learning maybe some variables have a stronger relationship to the outcome, a weaker relationship, etc. The elicitcausal app, if you do this, if you look at a causal graph before and after, it has ways of measuring essentially the amount of causal learning, or the differences in these two causal graphs. That can be very useful for understanding what you got out of your experiment. So I'm going to just work through kind of the basic steps of using this app and work through an example with you. Of course, if you open the app, there are instructions on the home page. There's no login or anything. It's just open to anybody. That gives you, I'm not going to read through them, but that gives you some more information as well. If you start, the first thing you have to do when using the app is to have a causal graph, is to define, the structure of the causal graph, meaning what variables you have, how they're, connected to each other. If you know how to use Dagity, the app can accept a Dagity causal graph, which you can, in that case, you can just hop right ahead to the Define Graph Pre-Study tab. But if not, you can just get started with this tab here that allows you to draw a causal graph with a sort of point and click interface that I'll show you. So, we'll start here. We'll say we have some outcome y. Oops, hit the Add Node button. So this will be the outcome we want to explain. We'll have another node. We'll call this one x. We'll say that this variable x is a causal factor for y by drawing an edge between them using the edge button. We'll add some more causal factors. So let's add one we call z. We'll put it up here, and we'll draw an edge for z. We'll add another node here. We'll call this actually our treatment, t. We'll say that t causally influences x, and t causally influences y. So in other words, there's both a direct effect of t on y and an indirect effect of t on y through x. Now this is sort of an abstract graph. Of course, what those variables mean will depend on what you want to use it for. But this is our basic setup. We have our sort of our treatment. We have x, which is essentially a mediator, and z essentially an exogenous cause that also causes y but is not connected to the treatment. So once we're done, and of course you can play around with it, you can also remove nodes and things if you want. You can hit this button here, use this graph in the pre-study, and then it will import that over to the Define Graph Pre-Study tab. And this is what that syntax looks like in Dagity format. And if you know how that works, you can go ahead and just edit it directly in that text field. Here's that causal graph again visualized for us. Again, the treatment has a direct effect and an indirect effect through x on y, and then z down here also affecting y. Now, one thing I encourage people to do when using the software is to provide some more informative names as well to the nodes, that sort of to the variables in the graph, that kind of helps you understand what's happening. So for this, we'll use a biomedical example where t, again, is probably our treatment. And one thing I should note is that all the variables in these graphs are binary, meaning they only have two values. And that's done essentially for convenience, but also to make it practical, because the purpose of these causal graphs is to formalize your general knowledge about a topic. They're not designed to incorporate all the complexity about different data distributions, continuous data. And so we dichotomize things to simplify them so that we can capture our general knowledge about this topic. Of course, you can have causal graphs that have more complicated data associated with them, but a binary method is a great way essentially to get started with codifying your knowledge. So for treatment, we'll have control and treatment. We'll call Z our external or exogenous cause age, and we'll just have young and old. Our mediator, we'll call this heart rate, and heart rate can be slow or fast. And our treatment will be, or our outcome, sorry, Y, will be heart attacks. So, either you have a heart attack or you don't. So this is just our pretend causal graph, right, for this biomedical intervention that should reduce heart attacks, we hope. And of course, you can have many more variables if you want in your graph. You can add as many as you want. And what this thing represents, is essentially our knowledge about what the causal structure looks like. What it's missing is the strength of these relationships and also the direction, right? If heart rate goes up, what will happen to the heart attack? What about age? We can also encode that knowledge in the causal graph, and we need to if we want to measure causal learning. So that's a lot of what this app offers, is the ability to encode knowledge about the strength and direction of those relationships. So that's what that button elicit probabilities does. Now, there's two different what are called elicitation modes. The default is ranking, which is especially useful when you have more than two variables in the graph. Because it allows you to rank if you have multiple causal factors, such as we have multiple causal factors for our outcome. It allows you to rank them instead of having to specify individual probabilities. The probability sliders is essentially more demanding. It's also much more precise. You can set a specific probability to signify the strength of a bivariate relationship. Ranking is sort of more general, but it really is necessary. Once you have four or more variables, it becomes really tricky to set all the probabilities based on existing knowledge. So that is my recommendation. That's what we'll use for this. What we start when we do a list of probabilities, the algorithm is going to move what's called topographically, meaning from the beginning to the end of the graph. So it'll start with these. We'll start with the treatment, it'll start with age, because these variables are not caused by anything else. Then it'll move to heart rate, and then the heart attack, and so allows us to specify the probabilities for each of these nodes in turn. So we'll get started here. Now, even though we specify ranking, we still have to specify the probability for any variable that's not caused by anything else. This is essentially its baseline rate in the population. So it says the prompt here is, in the population you study, how likely is T to be treatment? So if we have a balanced design where 50% of our subjects are assigned to treatment, 50% to control, then we'll just leave that at 0.5, which means 50%. So that's just, how likely is the treatment? For Z, this essentially is, how many of our subjects are going to be old, how many of them are going to be young, and we can also, if we're not really sure what that distribution is going to look like, we can leave it at 0.5, which is just, we're uncertain, 50%. If we think we'll have more old than young, we could make it larger. So here we can say, okay, maybe 60% of our sample is likely to be old. This isn't incredibly important, but if you have that information about those baseline rates in the population or sample that you have, if you include those, then it will essentially make the answers, the causal learning, more precise. So let's go to next. This is what pops up here. We have this ranking thing. And this is because heart rate is our actually first outcome. Heart rate is an intermediate outcome that the treatment affects on this indirect path. So we first need to discuss, what effect do we think the treatment will have on this mediator heart rate? So for ranking, it's going to give us three choices. Either the variable has no effect, it has a positive effect, or it has a negative effect. And that's all. We don't specify any effect sizes. We only have one variable here, so this is pretty easy. And we can say, you know, if you're testing a treatment and you're just uncertain, you don't want to bias it one way or the other, you can just leave it at no effect if you want. But let's say, you know, we already have some prior research and we have a prior belief that the treatment should be effective at reducing heart rate, so we can put T over here. Now, that's just sort of a relative ranking, and it has to be relative to something. So for all of these outcomes that have causal factors, you can set down here, this probability slider is essentially the baseline rate. And that is, it says here, how likely is X to be fast, or your heart rate to be fast, when all of its direct causes are at their slow value, meaning 0. So when all the direct causes are 0, what is this to be set at? And in this particular situation, when the treatment is 0, it means it's control, and so that essentially means what's the heart rate in control. And this can get quite technical, especially when you have more than one cause, but you can just leave this at 50%. It's just here in case you want to be more precise about these causal relationships. But leaving it at 0.5 at 50% always essentially works. And the treatment effect of T, this negative treatment effect, is calculated relative to that baseline rate. So we'll go to the next one, and now we're going to actually, given all these causal factors, now we have to decide how these things are all going to be related to our outcome of heart attack. So first, for the treatment, again, if we wanted to test the treatment and not essentially impose any priors, we could just leave it here at no effect, meaning like we're not sure if it has any effect. But let's say that we expect our treatment to have a negative effect. These other ones are a little bit easier. So for heart rate, if heart rate goes up, are you more likely to have a heart attack? Sure. And if you're older, are you more likely to have a heart attack? Yes. Now, if you have multiple nodes or variables within one of these categories, you can also rank them in terms of how strong they are. So we'll say that heart rate has a stronger effect on heart attack than simply being old, which kind of makes sense. And again, the algorithm is going to assign probabilities to all of these variables for the strength of the relationship, and it's all relative to this baseline here, where all causes are 0 or at their low value. In that case, the baseline here is 50%. Again, you don't need to modify that, but if you want it, if you know what you're doing and you want it to be more precise, you can do that. And all those treatment effects will be calculated relative to that 50% baseline. And again, if you want things to be more precise, you can use you can elicit specific probability distributions, and I'll show you how to do that next. So we'll hit done. Once we have done that, now we have a fully specified causal graph. It's going to show us here, these are conditional probability tables. That's the full, essentially formal statistical definition of this causal graph. They're kind of hard to read, but these distributions do sum to 1 to show that they are true probabilities. Now there are ways essentially of saving this causal graph. So you can either save it as an R object. That means it's something that can be loaded directly into R's statistical software. There's sort of a native format for elicitcausal. Elicitcausal is an R package that you can use, although primarily it runs this app. So you can save it in that, but you can also save it in the format for some other R packages. So causal queries is another package that does very sophisticated analysis of causal graphs. There's a whole book and paper about it. You can save it in Theory Tools. Theory Tools is a causal graph package also for R that allows you to add a lot of metadata to causal graphs and simulate from them. So it's also very useful for experiments. You can download the plot image there. And what that does is essentially once you have one of these R objects, you have essentially saved your graph, right? Which you kind of need to do because this is a web app. And once it's on your computer, you can then re-upload it into the app as I show you. But in addition to these R objects, you can also download essentially different sort of written versions of your causal graph, and this is specifically for the purpose of pre-registration. You can save it as a markdown, a Word file, a Quarto file if you want, with a CSV for the actual data. And that's designed to, you could kind of just pop that right into a pre-registration that you're working on. And if you save those original files, you can even use those. You can upload those into the app later if you want to update them. So it's another way of saving it, although that's only if you keep the file in the exact same format. And so that's why it's also good to download one of these R objects, because those are, code and very precise in terms of the graph definition. So that's what we'll do first. We'll save it right here. And then we have our result, and we can show kind of what this looks like. We can download a Word file as well. Takes a second for that to be produced. And yeah, so here's what it looks like as a Word document. Oh. Give me 1 second to pull it up here. Oh, okay, having some issues. Hold on. There we go. This is what it produces, a little conditional probability table that defines your graph and with the specification. So you can just copy and paste that right into your pre-registration as a way of saying, hey, this is what I know about my outcome before I did the study, before I looked at the data. And as I argue, there's a paper associated with this called holistic causal learning, and I argue that that's actually incredibly valuable information to have in a pre-registration, because it actually gives you some freedom to explore all these different relationships with your data without doing things like p-hacking. It's essentially providing full transparency as to what you thought about this outcome before you started working on it. But what we can do now is, let's say that we close the app, we go do our study, we come back, and we can hit refresh here just to make it look like it's completely blank. And that's of course why you need to save it, because if you refresh, then the app is done. So we've already done our study, and now we want to update it. So we can come over here to the Define Graph Post-Study tab, and there's this icon here to upload the pre-study file. So we'll come over here and retrieve it, and you can use the different things. We'll just say use this RDS file, and there's our causal graph. Pops right up. And again, here we can do another ranking if we want, or we can use the probabilities. Since I didn't show the probabilities earlier, I'm going to do that. And so here's our full definition, and we'll hit elicit probabilities. This we probably want to leave as is because it's a treatment. We can just leave this. We'll assume that yes, this was our actual distribution for how old people are. We could, if you wanted this to be more realistic, we could set that to over 65 and use the census data to make it more precise. And this is this is again our mediator, where this is the effect of treatment on the mediator, where we said that our treatment would increase. Our treatment would decrease, heart rate. So this is when the treatment is control, it's about 81% chance of having a fast heart rate. If the treatment is, if you're in treatment, then you only have a 19% chance of having a fast heart rate. So it's the treatment has a strong effect on the mediator. And that's what we pre-registered. So now we need to update it. And let's say that, unfortunately, we were wrong about our assumptions about how effective the treatment was. It's actually somewhat lower. That the treatment did have an effect on the mediator, but actually 35% of people had a fast heart rate, right? And again, this is all binary stuff. So when you're updating this or putting this information in, you kind of have to use your judgment, right? Or maybe dichotomize your data to get some of these numbers back. You know, that's why also, you can be more precise initially, but the idea here is to get baselines, causal graphs that you can then update to make them more precise. So we were somewhat wrong, but there is still this, treatment effect on the mediator. So we'll just say that's good. And here's what, it looks like for our outcome. And, there are a lot of different probability sliders here. This is because to understand, the probability of having a heart attack, we have to look at the values of all causal factors for the outcome, including the treatment, heart rate, and age. And so, if there are 3 causal variables, there's going to be 6, potential sort of combinations of the causal factors. So it's kind of a lot, right? And that's why we use the ranking initially to set that sort of thing. Here, just for the purposes of demonstration, I'm going to change some of these probabilities to show how it works. And we can look at some of these specific conditions. Suppose that we're in control, that we have a slow heart rate, and it's an old person. How likely is it that Y will be a heart attack? Fairly high rate. So let's say that our treatment was effective. It was particularly effective for people who were old and had a slow heart rate. So let's set that a little bit higher, right? So our treatment was even more effective than we expected. Now we can suppose that, and it will come up here. We'll say that we'll look for one that's more. So let's say that we're now in treatment. We have a fast heart rate, and we're dealing with young people. Maybe that one will leave the same. We wouldn't maybe expect our treatment to be very efficacious for that group. Let's come down here. Let's say, suppose that you're in the treatment group, your heart rate is fast, and you're an old person. Should our treatment be effective here? Let's say that, we did our analysis and we found that, yes, actually in this condition, the treatment is quite effective. So we'll reduce this here. So we'll say there's a lower probability of a heart attack, right, in that condition. And if you notice, when I move one slider, the others also slightly move. And that's sort of a constraint in the app to force them all to sum to 1. It does make it a little bit trickier to set the sliders to specific values, but if you play around with it, it is possible to do. But that's also to make it a little easier to use. And you can see here, if this is why when we have a lot of variables, it's easier to use the ranking conceptually, although this does give you a lot more control. And as long as you kind of can think about, understand what all of these different cases are, and can kind of compare them to each other, you can also do it this way. So we'll hit done, and we'll say yes, some of those probabilities changed. We can also download the result here as well. We have new conditional probability tables, etc. But we can also come over here now to the causal learning tab. And what this will do is it will calculate, it uses a metric based on entropy, which is a measure of statistical information, to figure out if what we learned. And it actually will calculate this both for the entire graph in terms of percent. So if we look at our total change, we became somewhat more uncertain. And that's maybe kind of surprising, but it'll break it down for us by different variables in our causal graph. And the treatment wasn't as effective on the mediator as we expected, so that this increased our uncertainty or our entropy. We have less information about how the treatment affects the mediator. We became less uncertain about how these different causal variables affect our outcome of heart rate or heart attack, sorry. So that's good, but these entropy changes counterbalance each other, so that we end up with one that is actually slightly more uncertain. And you may be looking at these numbers like, this is -30, this is +7. Why aren't we still in negative entropy? And that's really because these things all have to be weighted together, and the outcome Y has a lot more causal factors. So because X only has one causal factor, it actually contributes more to overall entropy in that sense. And that's really why it's a really good measure, because it takes into account, all those different combinations of variables. So, but, we can always still break it down here to the different variables, right, where we see that there were kind of different things going on in the study. And of course, we can say, look, we actually became more uncertain about the role of this mediator, but we're actually better at predicting heart attacks afterwards, right? So that's still really important. And this is sort of the summary measure of overall causal learning, but of course there's a lot more going on here. And really the point of doing this is to provide a way of summarizing what you learned from your study in very precise terms, but also to encourage you to explore relationships, right? This is a method that encourages you to then look and say, okay, what's going on in my experiment? Now there's many more things you can do with causal graphs, and that's sort of why these results can be exported to other packages for further analysis, or for simulating data from the causal graph. You can even update a causal graph directly from data. The causal queries can do that exercise. So there's many other things, but this app is designed to be easy enough to use that you can do some fun, pre and post study informative causal learning. So I encourage you to give it a shot. And if you have any questions, you can always reach out to me via my webpage. I have my email. And thank you so much for your interest in the package.